Thank you so much for coming. This is my first time speaking at Hackfest, and I'm very happy to be here. I really like Quebec. So I'll just start by introducing myself. I'm from Urbana, Illinois, where the University of Illinois is, about actually 200 kilometers south of the Chicago Blackhawks. So I'm a software developer, and I'm in a NASA program called the Data Nauts, where we got the opportunity to learn about data science. And so I'm interested in basically both data science and security. And I got very interested in finding an area where those intersected. And so I've been basically studying basically data science and machine learning and cybersecurity. And I would just like to share some of the things I learned. I was also part of the 2017 SANS Women's Academy, where I was able to earn 3 GIAC certifications. I'm Wayward 710 on Twitter, je parle mal le français. J'ouvre la bouche, tout le monde parle anglais. So I don't speak French very well. So actually, I'm curious, how many people have had a vendor talk about how their product uses AI or machine learning or deep learning? Anybody heard that from a vendor at all? Oh yeah, okay. Vendors never ever mention that, right? So then we could actually start out by just talking about what do these terms even mean? And so one way of thinking about AI, machine learning, and deep learning is you could look at it as this egg diagram, or you could look at it as it's been described as a set of Russian dolls, where basically AI is on the outside layer. It encompasses everything. Machine learning is a slightly smaller subset. And then deep learning is basically a slightly smaller subset of that. So if you're hearing the terms used somewhat interchangeably, it's like basically you're talking about sort of a subset relation. So basically, what comes to mind when people think of artificial intelligence? Nobody. I mean, I was thinking of the movie 2000, because Hal came to life in Urbana, Illinois, after all. Look, Dave, I can see you're really upset about this. I honestly think you ought to sit down calmly, take a stress pill, and think things over. It doesn't ring a bell with very many people. Okay. So basically, it's been described as the branch of computer science dealing with the reproduction or mimicking of human-level intelligence, self-awareness, knowledge, consciousness, thought, and computer programs. In other words, it's artificial intelligence is where a computer tries to emulate some things we think of as being part of human intelligence, so it doesn't really work quite the same way. So basically, machine learning, I put a definition up here. It basically involves a whole lot of math, statistics, and algorithms. And there are two major terms you're going to come across when you talk about machine learning. It's called supervised and unsupervised learning. So has anybody heard of those before? Okay. So supervised learning essentially you at some level start out with some hopefully right answers, right? You basically start out with a set of correctly labeled data that you use as training data. And unsupervised learning is more interesting. Unsupervised learning, you don't get to start out with correctly labeled data. You actually take this data set that you don't have any right answers for, and basically extract knowledge and patterns from those. So next thing, I think you probably heard the term neural network, right? So essentially, a neural network, it's modeled on the human brain. It's modeled on the idea of neurons, where it gets a certain amount of, it gets certain inputs, and basically if it gets a certain level of input, then it's activated and it fires. And so basically nodes in neural networks are kind of like neurons. They get assigned weight kind of weights and thresholds. So this is kind of hard to just, this is kind of a little bit hard to visualize if you're not familiar with it. So I've just got I've got a diagram. It's like, it starts with so the red stuff on the far left is are basically inputs. You're to get maybe multiple kinds of inputs. And then this thing called hidden, those are the basically those are the hidden layers. In this case, it just has one hidden layer, but those are kind of the neurons you think about, and then those actually feed to the input. So it's not necessarily a completely one-way process, because it tends to continuously get feedback, and it can kind of continuously gets feedback and kind of adjust its computation and weights and stuff until it gets closer and closer to the right answer. And that, let's see. So I got hopefully a video. This is really kind of neat. It's called it's at a site called playground.tensorflow.org, and anybody can use it for free. And I have put the link in my slides. But kind of easy to see it. This is actually an animation of a neural network in progress. You can kind of see in your browser. You can basically add the features that are your input features. You can adjust your number of neurons in your layers, and visualize the output. So I don't know. Can you guys see that very well from your where you're sitting, or but at any rate, I'm going to tweet out my slides after I get done, and the link to the site, if you want to play with it, is going to be in the slides. But if you continue to watch this, you can kind of see the inputs and the weights and stuff getting refined kind of in response to the feedback, as far as, and basically the input keeps getting better and better. Anyhow, that is the best I could come up with for just visualizing a neural network in action. And like, I feel really bad about doing a presentation without any memes. And but in some ways, this is very realistic, because like when people talk about machine learning, they think of it as some kind of like magic black box or something, and that's not really what it is. I mean, a lot of times that people, when they're working with it, they need to know what kind of data they're working with, and they're kind of continuously tweaking the parameters in the model and stuff to make it better. I mean, if you go to the site and stuff, you can even experience that as you tweak your inputs and parameters and stuff, you can get better and better results. So actually, deep learning very specifically refers to these neural networks. So basically, when they talk about deep learning, I'm thinking probably a lot of vendors have used that too. So that is very specifically referring to these neural networks I showed you in action. And they can actually be both supervised and unsupervised. So one thing that's very useful about this is a lot of times when we're detecting threats and bad behaviors, we rely on signatures, which are kind of like signs or descriptions with associated with the malware exploit's known behavior. And so basically, if you have a known threat, the signatures are very good. And the problem is the zero-day exploits and stuff. You usually don't have signatures to plug into like your IDS or your antivirus software. So basically, this is where deep learning comes in. And the deep learning is good for detecting like a lot of anomaly detection. It can detect basically user behavior issues. User and behavior anomalies. Like, for example, like they've been used to detect insider fraud, insider threats, and fraud and stuff like that as well. Excuse me. Excuse me. So This is just an example paper that I read. I found very interesting. So one application that's very common with deep learning, it's not usually associated with security, but you see it in a lot with deep learning is like natural language processing. Like for example, if you go to deepl.com, that could be even a lot of people consider that even better than Google Translate. But you don't see a lot of NLP in security. But Microsoft has found a very interesting application of this. So they essentially use this algorithm called word2vec, which is kind of a neural net that is able to take these words and kind of embed them in vectors that show show something about the context and how far apart they are from each other. And they call it contextual embedding. And they get some very good results from that. So a lot of times your like your PowerShell commands, they have aliases, right? And also, if you've got a malicious script, people will very often try to obfuscate it. They'll try to they'll try to intentionally make it hard to break down. And this actually turned out to be very effective against that. So this was just a somewhat interesting use case I found. So actually, skipping over to preparing the data. So you got a few things. So we talk about data selection and sampling. Sometimes you can use all the data, but sometimes if you've got a whole lot of data, like for example, your network flow and stuff, it's not you have too much data. It's not practical to evaluate everything. You have to come up with some way of sampling and selecting. Another thing that they talk about is feature extraction. So with feature extraction, so you've got this whole thing, you've got this stream of data or something coming in at you, right? Like let's say you're trying to look at your network traffic or something. Maybe you've got a PCAP file, and it's like if you're not going to say dump the PCAP file directly into say something like TensorFlow. You need to maybe decide. So what part of the network traffic are you interested in? What features do you care about? For example, are you looking maybe for certain payloads? Are you looking for going to certain addresses with going to certain servers with poor reputations that show up in a threat intelligence feed? And so essentially, feature extraction it's like you need to understand something of the domain and decide which features that you want to think about. And we're going to talk a little bit more about that later. And then with it, feature encoding and vectorization, essentially that just means that you need to represent things in a mathematical way that these packages can understand. And then there's something called normalization. I don't know, has anybody heard of that before? Yeah. So essentially with normalization, it's like you have maybe you've got two variables you care about. One has a much wider variation than the other. Well, if you don't normalize those, the one with a wider variation is going to have maybe a disproportionate amount of influence on the results. So actually, here's an example of a just normalized data. Like for example, you can see that there's a lot more the CPU utilization percent and the request percent. The scale is completely different, and so normalization you probably want to find a way to scale. It's a pretty simple equation. You just want to basically represent all the data on a scale from 0 to 1. And so here's an example of how we normalize some data. Okay, so a big part of machine learning with security is pattern recognition. Like for example, there's something called data mining, knowledge discovery, and knowledge KDD, which I remember that calling knowledge discovery and something. but that tends to discover like just unknown patterns that are located in the data. And sometimes you want to basically find very explicit characteristics about the data. And so essentially, when you talk about pattern recognition, you can say you've got these things, it recognizes it, it can extract certain patterns that are related to the known data you're passing in, and it can take those patterns that it's discovered and apply it to unknown data. So like, for example, you have like some known hostile traffic, or you've got some known malware and stuff. Like you can feed it to a machine learning system, and it can extract characteristics about it, and then you can start feeding maybe unknown software or unknown traffic to it to say, well, does it look like this? And it's like, so does it look like this bad stuff you saw earlier? And so there's a lot of them. I think some of the most obvious are just your spam and your botnets and your malware. So basically, with clustering, the whole idea with clustering really is that bad things happen together. So let's see. I don't know if you want to think about this or not. Like, so if we, the audience, I mean, the remaining audience, and you needed to arrange yourself into clusters, how would you do it? I mean, it's like, so maybe you would try to find people, who are sitting close to you and arrange yourselves in groups. Instead of going across the room, maybe you would do it that way. And so a lot of times clusters, it's like you're trying to find points that are close together, and there's typically mathematical ways of measuring closest together. You can do it the Manhattan distance, or you can do the Euclidean distance, but that's usually pretty straightforward. And so the whole idea is that basically, so that the items within a cluster are going to be hopefully more similar to each other than items that are not in a given cluster. And so there's really a lot of ways you can do this. There's something called and we'll just talk about a couple of the most common ones, very common ones, called k-means and db-scan. Let's see. So the whole fundamental idea with k-means is you kind of try to group data points together and discover underlying patterns. So, I mean, essentially, you start by you start by just picking in like just putting centroids in arbitrary locations, trying and iterating through until you can discover the optimal the optimal location for the centroids. So it's a fairly simple algorithm. So this is just a picture of how it works. So initially it's kind of random. That's not very good. Round 1 gets a little better. Round 2 gets still better, and then finally you get basically an optimal, like you get what's a pretty good cluster. And then another approach you can take, it's this is really common. It shows up very often in like research papers about machine learning and security. It's called db-scan. And honestly, I keep thinking of it as being about databases, but it is not. It's about density-based spatial clustering of applications with noise. And then the noise is significant too, because you actually want to find the noise. So basically that takes 2 parameters. Basically it's EPS, also known as epsilon, that specifies how close the points should be together to be considered part of a cluster. And then min points is basically what's your minimum number of points that could be considered a cluster. So you pass those 2 parameters. So it's basically it's an iterative process, just like k-means. You start with an arbitrary point. If you can start to form a cluster, you do. If you cannot form a cluster at the point, label it as noise. And basically you kind of continue this until you've built your cluster, and then you restart with another point that has not been visited and do the same thing until you basically have a number of clusters. One thing that's a bit different about db-scan is that with the k-means, you have to tell it how many clusters you want, and that actually involves a lot of that does involve some trying and error. DB scan will come up with a number of clusters for you. So you are possibly going to want to tweak your parameters as far as like your epsilon and your minimum number of points. So this is just showing your DB scan cluster in action. So I don't know how well you guys can see that. You've got yellow, green, and red, and then you've got these points on the outside that are kind of black. And those would be considered your noise points. Okay. Okay. So actually, just as far as some case studies, I found some rather interesting ones from Trend Micro and Semantic. So the semantic basically is that Semantic actually started with looking at the HTTP flows and trying to look for things that were consistent with known malware attacks. And so we talked earlier about features, like what do you care about? Features, a lot of times it's like, what kind of information are you trying to extract from this that you might care about? So there were actually a couple of very significant features. When they were trying to find attacks that they could cluster as ransomware, that very often showed up in the URL. That basically they were able, the URL information gave them allowed them to cluster ransomware attacks together, which is pretty interesting. The other ones were generic malware, and what that was actually more related to the payload, because that was specifically the file type. So that was related to like your file type. The malware was coming across and stuff like PDFs and Shockwave and stuff like, and basically files like that, which is a pretty normal way to deliver malware. And then in Semantic, they did something kind of interesting. They basically Semantic is running their SOC, and they want to basically cluster the incidents that happen in their SOCs together. And so they want to basically see like how similar events are. Like, so can they respond to them in a similar way? Can they learn anything from how they're handled in the past? And they actually were able to, they actually had quite a bit of success. Like, they were able to figure out, like, for example, if they got like a malware attack, they were able to cluster a lot of things that came into their SOC with that malware attack. They could also look for they also were able to look for certain behaviors that were not good. Like, for example, like if you're monitoring a network, if somebody's attacking you, what kinds of things might they do? They might start scanning you, right? Like they might start looking for vulnerable services. They might start looking for, like, do you have an open SMTP server? Do you have services like FTP or LDAP or something that might be vulnerable, that could be abused, or provide some information for them? And so they were able to look at that as well, to see just known they were able to look at that as well, and cluster those kinds of attacks together as well. So just as far as clustering takeaways, they can be applied to a lot of different kinds of data. Like, for example, categorical and continuous. When they talk about the relevant features being extracted and normalized, and that does mean that you probably need to know something about the domain and the data you're dealing with, so you know what kinds of features you might want to extract. And there, basically, a lot of times with machine learning, there are validation techniques. A lot of times, if you're trying to validate a cluster, you maybe look at the cluster and you see, you basically look maybe how close the clusters are. How does that how many elements are in clusters? How does that perform to other clustering algorithms? there actually are some ways you can validate that. And so basically what it the way it works is really kind of what it did with the SOC and the network. It's they started with, like, a big SOC is going to have lots and lots of data, and it allowed them to basically take this vast amount of data and sift through it. Okay, so classification, it sounds kind of like clustering, but it's a bit different. So basically, classification is like what is the likelihood that something is in a given class. So, like, if you were going to classify people here, any ideas how you would do it? Okay, like haves versus leaves. No, sorry. But essentially the classification is a little bit different because it's like you know what classes or categories you want to use, and that's actually a little bit works a little bit differently than clustering. And so that is basically considered a supervised learning because it's kind of like you're starting with the answers. The samples have already been correctly labeled and identified. And then it's also possible, just to bear in mind with classification, that a sample can belong to kind of multiple categories at once. So just some classification, just some examples of, here's an example of what somebody did. Just as a classic example, they wanted to detect a botnet command and control center. So what they did was they issued a HTTP request to benign and CNC controls. And so, actually, let me clarify that. What they did was they took a list of files and file headers and URLs that were known or associated with kind of known sketchy CNC sites. And so they specifically requested those and they saved the responses and of course the response codes. Cause, like, for example, if you get say a 404 or something, that would mean that the file wasn't there. And that's different than if you get a 200 and you get the file right with an HTTP request. So they were actually able to create a decision tree model, and they basically saying essentially if they get if they got enough hits on the sketchy looking file patterns, they were to conclude that it was fairly likely that this was a CNC server. Classification. So essentially, it's a supervised learning. While it can work well when there is a sufficient quantity of accurately labeled data, and one challenge in security is it says if there is a sufficient quality of accurately labeled data. So in security, that's not always the case. And so essentially, you've got the 4-phase methodology, you've got the training, and then the validation, where you do something to actually test to make sure whether your model makes sense. A very common way of validating in machine learning is that you take your training data, but you withhold some of it, you keep some of it out of the training model. And then you run your model and you generate your model, and then you take the data that you've held out against it and you see how well that performs. And that is a fairly, like, saying, so does your model still hold up when you test it with this new data that you haven't used in training? And that's just a very common way you do your validation. Another thing with classification is you're not getting absolutes. It's not going to say this is absolutely a CNC server or this is absolutely a botnet. It's basically to tell you how likely it is. And so a big known problem with, like, machine learning is you get false positives and false negatives. And so, like, false positives are like when you get an alert, it tells you that there's a problem and there's not. And false negative is when it tells you that something is okay and it's not. And so a problem with the false positives in security is that it can chew up a whole lot of your time. Like, if it's constantly going off and throwing up alerts you have to deal with, it can waste a lot of your time, and it can teach people to ignore. It can teach people to even ignore the system. And false negatives are kind of obviously a problem I mean, because, well, it means the system's not doing what you want it to do. You want it to tell you if there's a problem, and it's not. So those are actually both big problems, and they're both risks with machine learning. So this is actually a little bit different. We talked earlier about pattern recognition. And so the idea, like, what is normal but a state of mind? So the whole idea is that we want to establish some rough idea of what normal looks like. And when we talk about this deviation from normal, we can call them anomalies or outliers. And in security, anomalies, something that's unusual is often bad. And so, for example, like, anomalies often mean that we have like an intruder or a breach or an exploit going on. So just your overall goals with an intrusion system, just for the reasons we talked about earlier, you want low false positives and low false negatives so that it does its job without wasting a lot of people's time. I mean, the whole reason you're going to want to plug machine learning in is basically to save people's time, to automate, to maybe ideally automate some of the tedious tasks that your SOCs are not going to want to spend their time doing. You want it to be basically easy to work with. And it's just with exploits and threats and stuff. The landscape changes constantly in security, doesn't it? I mean, it's like your latest worms, your latest alerts. Like when is the last time there's a security alert? Probably today. And ideally like resource efficient, because it's with security, you can be talking about very large amounts of data. And in fact, some of the security, the software and stuff specifically uses tools like Hadoop and stuff to deal with big data. And there's also something called explainable alerts. Does that make sense? I mean, essentially, you want to know if it's telling you something's wrong. You want to be able to trace back why it made that decision. Like, for example, if it tells you to delete somebody's account, that person is maybe going to want to know why their account got deleted. So you're going to want to be able to understand the system well enough to know why it did what it did. So let's just talk. So we talked earlier about just features and stuff and what we might want to look for. And these are some things you might want to look for in host intrusion. I mean, so you're going to be looking at processes. Are you seeing anything unusual? And sometimes processes on an attack are camouflaged to look pretty close to something that's normal, like just a little bit off. Anybody seen that? You can see active new user accounts. Like, it created this account. Why did it do it? Is it loading any kernel modules it doesn't usually look? And then actually your DNS can tell you quite a bit. Is it like, for example, is it looking up sites is it looking up locations or addresses that happen to be also showing up on your threat intel feed? So DNS lookups can actually tell you quite a bit. Network connections are kind of important because it's like if you're trying to connect like a command and control network or and just a lot of times if you've got a compromised system, it should be trying to communicate out, right? And then another thing that you'll see is like, for example, with a Windows attack, it's going to try to modulate. You're going to see your registry database messed with often, right? Or that's not uncommon when you get like a Windows malware attack, is it? This is a fairly useful tool if you want to actually look at your host to see what may be compromised. I think probably a lot of you have heard of it, OS Query. Yes. Okay. So it's fairly handy. You can run query. You can schedule queries. It'll populate tables. You can query later. It's I believe it's free. It runs in it supports Windows and Linux. And that is just a very good way of getting information that you might want to feed into a machine learning algorithm. So another approach, network intrusion detection. As we said earlier, a lot of times if you've got a compromised host, it's going to in some way try to initiate communication with the outside world. And like whether it's exfiltrating data or if it's talking to a command and control server. I mean, your adware is trying to download ads to show up on your machine. Your spyware is sending the results of your monitoring somewhere. And you can. There are a lot of tools. You guys have probably heard of them. TCP dump. I bet everybody's heard of. Yes. Okay. And then Snort's fairly simple. Snort's pretty popular and it's fairly simple and rule based. And then there's also a tool. I don't know if you guys heard of Bro. Okay, Bro is now known as Zeek. And that's kind of neat. That's like a Bro is actually kind of like a programming language specifically dedicated to monitoring and analyzing network traffic. It's pretty impressive. Okay, so another thing that very often a very common target, it's called your web application. It's your web application. So these are some things you might want to look for to feed into a machine learning algorithm for a potential web intrusion. So you might want to look at your IP addresses again if it's connected to if you're seeing sketchy IP addresses. One thing you could possibly do that's sometimes helpful is also geolocate IP addresses. I mean, if you're getting a lot of logins to your small company network from like China or Romania, maybe that's not good. You see kind of some, and sometimes you'll see some kind of strange URL strings. You'll see null terminations or decoded URLs or whatever, and they're essentially trying to evade signature. So they're doing funny things with strings to try to evade signature-based detections. And then okay, so like your unusual referrer patterns. I mean, has anybody here used curl? A few of you, right? Okay, so curl's kind of a nice tool. You can connect. It's a very nice way to connect to a web server via the command line. And you can pass in a lot of parameters. And so it's like if you're using curl, you can tell it that your user agent or referrer is whatever you want it to be. And so, like for example, if you're seeing somebody who's using Mozilla from 1998, it's possible that some of that information is getting manipulated. I mean, if you're seeing something that's really old or really strange, it's possible that somebody's manipulating something. So when they talk about sequence of access to endpoints, has anybody heard of fuzzing? Yeah, so like fuzzing is when you throw a whole bunch of inputs at something to try to see if you can make it somehow. It's to try to see if you can make it fail or expose some kind of security hole. And so when you start seeing these really strange sequences of access to endpoints that are not consistent with what a normal user would do, it's possible somebody is throwing a fuzzer at you. And so one of these things is these are all the kinds of things you might look at to feed into a machine learning tool. And just for what it is worth, again, I'll post my slides online and tweet out the links the links. So we've got another tool called forecasting. So we've probably all heard of forecasting, like in terms of weather, right? And so you've got things called trends, and then seasons, and then cycles. And that kind of means that you're going to see some up and down and stuff in cycles. You're not going to necessarily see straight lines up and down. I mean, and so let's see. So basically, this is just basically a model that handles basically a forecast. These are also described as time series because it's like a lot of times they're something that happens over a time. And then so we've got something called ARIMA. It's the auto regressive integrated moving average. And so that basically means that these models are kind of dependent on kind of their own past input. So it's basically what it gets. It simply gets its input from what's happened in the past, but it's somewhat more sophisticated than a linear algorithm, because a lot of times, like if you see a time series trend, it's not going to be linear. Like for example, if you look at usage or something on your work network, you're hopefully not going to see as much going on maybe in the middle of the night as you would during the middle of a workday. So you're not going to, so your usage is not going to be a straight line. It's going to go kind of up and down, right? And then, so this is just a generic data series. You can kind of see that's it's basically a daily series that goes up and down, but it's kind of trending up. But you can kind of see that it's through the regression line that so it's got its cycles, but it's kind of trending upward, right? And this is just an example of basically a time series that you can apply forecasting to. This is a generic thing. Well, what do you want to talk about CPU utilization over a period of time? So let's say this is a graph of some known CPU data. And so actually you can apply something like ARIMA, or in fact another forecasting model, to try to get an idea of what's normal, what can you expect on a particular time based on what's happened in the past. And so I don't know if you can you see the can you see the blue and black from there, or not very well? Okay, so basically the blue is the actual data and the black's the model. And so you see they managed to fit that pretty well. So what we're going to do, I think we talked earlier about, like, a lot of times you want to, like, sometimes you want to validate, or you want to test your model. We're going to go ahead and take some data that's not in a sample, or we're going to apply this model we came up with in the last slide. So this is what the model looks like. You can see it's kind of blurry at the end, and that means they're not quite as confident about it. That means that they're a little bit hazier about what happens. And then this in the gray shows the area. This in the gray shows the area, and you can see that the area, so you can see that the area does not line up very well with what was forecast. So the area, that gray area and stuff, doesn't line up very well with what was forecast, because if you look at the model in the past, it was trending upwards. It was gradually trending upwards. And the area in the gray, it's starting to drop, and that the upward trend wasn't continuing. So it's like basically through this model, we can see that was viewed as kind of an anomaly. Does that make any sense? Okay. So I'm sure, has anybody here not heard of like a malware family? A family of malware? No, yes. Okay. So like a lot of times, like you get this malware comes in, and then you start getting these other samples of malware that are maybe a whole lot like it, but not exactly like it. And it's like maybe they're building it on different compilers. They're trying to evade signatures or something like that, but it's really kind of the same thing, doing the same stuff. And that's what they mean by a malware. That's what they mean by a malware family. In fact, like it's probably coming from the same people. So traditionally with malware, like your typical antivirus thing, you've got the signature matching. It matches kind of known characteristics of this malware. And that's great, except for what about when you get the 0 days? So you can use things. Have you guys heard of static, and you don't understand what static and dynamic analysis means with malware? It's like static analysis, you're basically taking the binary and just the executable stuff and analyzing what's in the executable. And dynamic analysis, it's like you're taking it in like a sandbox, often like a VM or something, and executing it. So let's see. So with Android malware, you might look for interesting strings, specifically like hard-coded URLs and addresses that it might be using to talk to a CNC server or some other malevolent server. You might look at what kinds of API calls does it make. The network, I mean, just when you're looking at it dynamically, it's what kind of network behavior is it starting to try to initiate these connections, and if so, why? You want to look at what's changed in your system. Like, have you seen strange changes to your registry that don't make any sense with that kind of software, with what the software is supposed to be? And that kind of stuff. And for example, and if you're looking at say something like Android or something, you can also look at like Android. You can actually just look at the manifest and see if it's requesting permissions that greatly exceed what it would need to do that kind of thing. Because like a lot of times, for example, people with mobile stuff, they'll agree to just about anything. I mean, seriously, have you seen the permissions and stuff where you're trying to install something on your phone? It's like, yeah, I'd like to access your email address, your contacts, and then I'd like to have your firstborn child. And your users are just like, okay, okay, okay. And so basically, strange permissions in mobile applications are kind of a common malware delivery route. So let's talk about so we've talked about what machine learning is. Should we talk about what some of the limitations of it are? One, we talked a little bit about it. We talked a bit about explainability earlier, and it's like, so is your machine learning system this black box, or is it like, can the analyst actually explain, understand why the system made a particular decision or recommendation? It's also not a silver bullet. I mean, like, your vendors are talking to you and they're saying, we've got this machine learning and stuff, like it's going to be magic. And it's like, it's really not. There's nothing magic at all about it. It's basically a set of like mathematical techniques and algorithms. And you have to know what you're feeding into it if you want to use it. Another thing that the body of human knowledge is just pretty large. Like, for example, like if you're trying to decide whether an email is spam or ham, like a human could look at it and understand words and context. Like maybe if somebody sends you, like you're doing business with a vendor and they send you an email about the laser toner you've ordered, that's legitimate. But like a lot of times, cheap laser toner in an email, it's not good. Right, and there are a whole lot of other words that often show them as spam emails, but they can sometimes show up in legitimate emails, and a human can pretty readily look at them because it's like there's a whole lot of background knowledge and context and stuff, and it can be hard to represent that to a machine learning algorithm. There's also, have you guys heard of overfitting and underfitting? So overfitting and underfitting is like when you have some training data. Sometimes it may be when you overfit it, it means it fits the training data very well, but it doesn't generalize to other data very well. Underfitting means that it doesn't really fit it doesn't really fit any of the data very well. And generally just like with anything in a computer, machine learning, it's garbage in, garbage out. I mean, it's not specifically related to security, but okay, have you ever heard of like algorithms that deal with different races of people differently, like a smart sink or something? They've only tested it with people with light skin, and somebody with dark skin tries to use it and it doesn't work. And very recently there was an article about like an algorithm that recommended like lower quality of care for African Americans. So essentially the thing that is, it's not a silver bullet, and basically garbage in, garbage out. There's nothing magical about it. So right now I just have some links and stuff. If you want to dig into it yourself, you're welcome to. And I'd like to heavily credit these are some excellent resources. This is Machine Learning with Security, Protecting Data Systems with Data and Algorithms. This is an O'Reilly book. It's excellent. I got it in a $15 humble bundle purchase, at least the electronic version. The Silence book is pretty good, and that's actually free. So it's like you can get these for inexpensive or free, and they're very good. I would say I use these heavily when in the talk. And then there's Towards Data Science, which is a website. That's pretty good too. And then these are just some other good resources you might want to use when you At any rate, thank you for your patience. Are, are there any questions, or are we pretty much at time? I think we're at time, but if you have any questions, you're welcome to come up to me. No?
How many time you can spend on data classification before just sending that to your machine learning process? Because it seems to be critical. If the data is not good, like your entire process at the end will fail, or like don't do what you want to do, or how do you acquire like good sample of data? Or
To be very honest, like, so if I was to start doing like some machine learning, and I knew nothing about the domain and the data, what I would really do is basically hit Google and see if anybody else, see what kind of analysis, maybe not even machine learning, had been done on that data before. What do people look for, and try to learn something about the domain and what's been done in that. That would just give me a starting point. Because like if you just try to throw something that you don't understand at a machine learning algorithm, that's going to maybe not work out very well. And one thing you can do, I tried to show some graphs just because I mean my presentation, it was pretty mem deficient really, and I figured we could at least have some graphs. And it's like if you're dealing with 2 and 3 dimensions, it's actually very useful to just visualize it, like just graph what you have and say, does it make sense? And you can kind of do that in 3 dimensions too. Once you get past that, you get into hyperplanes, and that's kind of hard for humans to process.
Hello, sorry. One common problem that what I've read and seen while implementing machine learning, not necessarily just for security, but for any domain, is there's a bias in the data.
Oh yeah,
especially when they're during the stage of gathering the data. Is that also a prevalent problem when it comes to security domain?
I would imagine it could be. I mean, I think that when we talk about bias and stuff, like in some ways, racism is kind of a most obvious and glaring one that we've seen, like in other domains of data science that are not related to security. But I would say, if you think about bias in terms of like preconceived notions and just preconceived notion about what you should look for and what's important, I would think somebody could introduce bias into that very easily. Just in fact, even just what somebody knows and what's familiar to them. Does that make any sense?
Yeah, and so in your experience, what would you actually recommend in actually cleaning up that bias or making sure it's not introduced further down the pipeline?
That's actually very interesting. That's an excellent question. And the best thing I could maybe think of is trying to see if somebody else has approached the problem a different way, and comparing your approach to their approach and seeing if they saw something or thought about something in a way that you didn't. Because it's just like as far as trying to get past what's in my own head, I feel like the best thing I can do is try to find some kind of external input.
Thank you.